Okay, folks, let's get into these specific reaction order types. So with Learning Goal 8.4, we're going to get into the properties of zeroth order reactions. And you notice here I've got a little Mathematica demonstration for us here, both a static plot and a manipulate plot. So in a zero order reaction, there is no concentration dependence on rate. No concentration dependence on rate. So in other words, if I go to start setting up the rate law for this thing, I could start by saying negative dA by dt. So putting together the rate with the stoichiometric coefficient equals k times a to the 0th power, which means that's going to drop out and the rate will just equal the rate constant. Okay. So doing some algebraic rearrangement, we typically are going to start seeing these things written with the negative or the positive sign on the other side of the equation to set the rate to a positive quantity. And we do that to make the integration a little bit more straightforward. So now the way that we are going to handle this, we're going to separate into the two sides. So dA equals negative k dt. And now we're going to integrate this from some initial concentration to some final concentration. And we're going to integrate this from some initial time to some final time. And this one, as you might guess, works out to be pretty straightforward, right? So what we end up with here is the integral of dA evaluated from final to initial is just going to be a final minus a initial. And then now, because the way that this works, we're not going to really consider this as t final minus t initial. We're just going to consider it as how much time elapsed. So now this part of the integral just becomes negative kt. So now, as is pretty standard, I'm going to rewrite this algebraically to be consistent with what's done in literature. And in literature, we would typically see the final concentration just written as that, just as bracket A. And the initial concentration we typically see with a little 0 written right there. So just to make sure that we're consistent with literature, this is now what our integrated rate law would look like. And doing just a little bit more algebra on there, we can see the concentration of A at any time is going to be equal to its initial concentration minus KT. And so now if we were to make a plot of concentration versus time, you can see my y-axis is concentration. I end up with an intercept, I'll write y-intercept, which is the initial concentration. And then now that's minus slope times x, where now the slope of my line is the rate constant. And that's only true for a zero order reaction. So in this plot, I also considered what would happen to the products. So in this plot right here, the reaction is A goes to B, both of which are zero order dependent. So, and you can see the slopes are one and the same, just opposite signs. So now for the reactant, it's technically a negative slope equals the rate constant. And now for the product, it's a positive slope equals the rate constant. Okay. And if we were to look at what happens if we increase or decrease the rate constant, we can see right here that those slopes change. So if I decrease the value of the rate constant, you can see barely any A decays and hardly any B evolves, right? But if I increase the value of the rate constant, you can see those slopes increase dramatically. And now in this zeroth order reaction, you can see when the concentration of A hits 0, the concentration of B hits 1, and that would indicate that the reaction is done. So the reaction is over with much faster with a larger rate constant. The reaction takes longer with a much smaller rate constant. Okay, so hopefully that makes good sense. That's all that I'm going to say about zero order reactions. see you in the next video.